So I still have to give my spiel about this for two reasons. One, so that the video can know, but also two, because I the topic I was about to get to in my other class would be way too overwhelming to end the class on. So I need to soak up a few minutes to not. Anyway, so this is the first time I've taught this. Well, now it's technically the second time I've taught this topic. It's You're gonna have to let me stumble a bit. I might make mistakes on the board. I have to look at this a lot to like remember my examples because I made them over the weekend. Um, so it's a bit challenging. It's not that I've never talked about graph theory before. I've talked about it for ages. And especially when we're talking about trees, my undergraduate started in computing science, so I know all of that stuff like the back of my hand. But I've never formally taught it before, so it's taking some getting used to talk about this language. So please forgive me. But at the end, so not at the end today, but like on Wednesday, I'm going to try to pick what I think sounds like the most fun things to do for a quiz. And then after I give you the quiz and you do it, I'm like on not next week because it's reading week. Hooray! But the week after that, I will probably say like, okay, well now that you've had some time to think about it, which exercise did you think was fun? Which part do you like? What should I spend more time on? What should I spend less time? Like, just get feedback because I don't know. Um, but if the feedback is, well, I was about as interested as the rest of the course, then I'd be like, I'll take it. That's a win to me because that means it's fine. But anyway, I'm really excited about this topic. I like it a lot, and it's got a lot of applications to computing, so that's why it's fun. Anyway, I don't have any specific announcements other than the quiz is due tonight, but I think pretty much everyone's already handed in it either online or to me physically. So, whatever. Just figured I'd mention it. And last class, we spent a bunch of time talking about recursion because we only had one class last week. I tried to think of a topic that, like, hey, what can we talk about that doesn't totally disrupt the schedule but is still interesting and relevant? So I was like, recursion seems to fit in, and we managed to do it. So we gave quite a few examples of recursive functions, which again are functions that refer to or call themselves in their definition. And I defined the factorial in terms of recursion. That's terrible. Don't do that. It's a bad way to do it, but it was just an example. Finding the GCD, though, is generally defined recursively. You can do it iteratively if you want. I had some like weird academic ones, but the Fibonacci, this is one I didn't present, but I'm going to do it right now, is typically an important sequence of numbers. So it has two base cases, 0 and 1. They're just both 1. And the nth Fibonacci number is just the sum of the two preceding ones. So this is an important sequence for many reasons. One, it's the worst case scenario for the GCD algorithm, so that's interesting. The ratio between Fibonacci numbers, when you actually calculate it, ends up being something called the golden number. It's just a very specific constant that appears a lot in nature and mechanics. So if you think of like a spiral, certain spirals that appear in nature actually have that as a ratio. It's kind of neat. So these numbers appear all over the place in nature. I just think they're kind of cool. So let's get to our next topic, and that is graph theory. Like I said, this is brand new for me in this course. I think it's a way better fit than proofs, like way better. And if I showed you the exercises and notes for proofs after this, you would say, yes, I agree, Travis, because that looks awful. So when we say graph theory, this is an important note. We don't mean, graphs like that, right? Not like this at all. This is a graph too, but this is a graph that's sort of continuous. By continuous, we mean I can draw this without lifting my pen, and it's sort of like a continuous line, right? There's a notion of discrete, which would be like dots like this, right? Like very specific finite number of dots. This sort of captures like an infinite amount of numbers in a sense. we're talking about something discrete. Graph theory is a branch of mathematics called discrete math. And in fact, in the process of quote unquote redesigning this course, like figuring out what topics fit and what don't, I'm probably going to turn it into a discrete math class. So there's none of this calculus stuff. It's all stuff like that. Because computers are discrete, right? They work in finite amounts of memory and space, so discrete problems are applicable. So sort of the nature of this section, because I only have a week for it, I just kind of want to give sort of a broad strokes overview of the various types of things and get feedback on what people found interesting, is that it's going to be kind of rapid fire definitions that we might not get to spend as much time on as I would like, but none of the definitions in this are particularly ridiculous. Most of them, because it's a discrete math topic, are actually pretty down to earth. Like they mostly match intuition. So let's start with a definition, and that is of what a graph is. So a graph, just like with sets, we'll usually use a capital letter for it, G for graph, is two sets kind of together as one. So the first set consists of something called vertices. And just in passing, I'm trying not to do this. I may call them nodes. You may also call them points. Vertices is the math word. Nodes is more fitting for computing science or just programming. So you might see them used interchangeably in resources and also by me just accidentally, because if I start talking about trees, I might start saying nodes. But it's a set of something we're calling vertices. And that's all we need to say about it. So what it is it's just a collection of points, right? And we can label them however, rather than points, think of them as labels, right? It's just a set of labels of things. Another set is that of edges, which we're going to call E. E for edges, E for vertices. So what is this set? This one has a bit more information in it. This set consists of unordered pairs of vertices. So it's just sort of a set of pairs of vertices. So, okay, two things. What's this really saying? Let's do some examples to sort of explain that. But also, too, we're calling it graph. So that means there surely is some kind of visualization of this, right? Otherwise, that would be a pretty bad name for it. So let's write down some examples and then see if we can figure out how they're visualized. So let's suppose that our vertices, our V, has four things in it: A, B, C, and D. See, this is what I mean. It's just a set. It's a normal set of just stuff. And our edges, okay, so this is a set of unordered pairs. So this one's going to look a bit weird. It is a set of basically sets. So the one I have here is A comma B is our first one. A comma C is our second one. And A comma D is our third one. So, okay, that seems like we're calling it a graph. What's the connection here? Well, we have these things called vertices, which we can represent as sort of discrete points, right? This is A, B, C, and D, right? These just sort of points. They're dots. Now, this edge is sort of, the word edge kind of makes sense. This is saying, hey, there is an edge connecting A and B. So A comma B says, hey, A is connected to B. This one is saying A is connected to C. And this one, A is connected to D. And with that, now you can kind of see why this is maybe more called a graph. I mean, it's hard to picture it as a graph because from high school, we're just so used to graph meaning things in the plane, right? Like you plug it into your graphing calculator. But in some sense, this is a graph too, right? It's some points being connected together, right? That's why we chose that name. It's just when we're graphing in our graphing calculator, it's infinitely many points being joined together, so it looks nice and smooth. This is just a set number of points being joined together. Okay, so let's call this graph 1, just in case I sort of start writing notes down that aren't connected to the graphs. All right, let's do another example. Because there's a lot of different ways to sort of classify and subdivide and split, like explain different types of graphs. So we're going to kind of do that here. So suppose our vertices consist of just 3 vertices, A, B, and C. Okay, so in terms of a graph, we can already draw that. A, B, and C. That's our vertices. So now the edges just tell us how to connect these together. And E are edges. And there is going to be a minor issue with this initially, and I'll explain it. So we've got A comma B, A comma C, and C comma C. So already this seems kind of odd because we've mentioned when we're talking about sets, we remove duplicates. So this is technically called a multi-set. We're not going to focus in on this type of graph very much. I'm just trying to show it for demonstration that this is technically also a graph. So let's try and think of what's going on here. This is saying A is connected to A. So all that means is we start at A and just go back to A, right? This is saying A is connected to B. This is saying A is connected to C. And this is saying C goes right back to C. Right? So the only sort of issue here, and the reason why we're not going to focus on this one, is again, we have both in programming and in mathematics, sets only contain distinct elements. So this one already seems kind of bad. But in terms of graph theory, this is a valid graph. So I'm just going to put in parentheses here, this is usually with multi-sets. But this is a totally legitimate graph that you can draw. The third one doesn't have this problem, thankfully. Suppose we have 4 vertices again. And our edges, so it's going to be A comma B and C comma D. So there's 2 edges. So okay, we've got A, B, C, and D. And what this is saying is we have a connection from A to B, and we have a connection from C to D. So these 3 graphs kind of have some standout differences between them, right? In some sense, this graph is what we would call good, right? This is a well-behaved, nice graph. Because there's 2 sort of standout features here. This one has these sort of loops, right? Things connected to themselves. And in some sense, that's sort of degenerate. We don't want that. That's kind of bad. Bad in the sense of talking about a bunch of algorithms we want to talk about. It's not bad in the sense of applications, right? There are lots of situations where vertices will be connected to themselves, But in terms of what we want to talk about, that's not a good situation to be in. Same thing here. We look at this, and we've sort of got this whole thing together, taken together, is one graph. This is a graph. But we have this sort of, two distinct pieces there, right? We've got this sort of chunk here and this chunk here, and they're not really connected to each other, right? At all. They're sort of distinct. Also, I'm noticing that I fixed it. That was cut off. So we want to sort of give this and this a name, essentially so that we can avoid it. So this one right here, I'm gonna erase this so I can write down the definitions. Because this is a nice graph. This one's fine. So a graph is called simple if it has no loops. That's it. So this graph right here, not simple. The first one was simple. This one also simple, right? There are two chunks here, but there's no loops, right? There's nothing connecting to itself, right? When we say loops, we mean connecting to itself. I'm going to actually say vertex connected to itself. Okay, so this sort of classifies this type of graph, which we want to avoid. This one over here, a word that I would describe this with is disconnected, right? This is disconnected from this, right? They're not connected at all. I can't go from here to here. So that's how we'll define it. A graph is called connected if, given any vertex, there is a path from that vertex to any other. So in a sense, you can start anywhere you'd like and get anywhere else you'd like. Maybe that path is really bad, but you can do it. Right? So this here, not connected, because I can't go from A to D, but this is connected. Because I can go from B to A to A to A to A to A to C, right? I mean, like I can loop around this as many times as I want and get here. Or you can just go B to A to C, right? So you can get from any path to any other path. And the other graph was also connected, right? You could go from any node or vertex to any other one. So in terms of this section, when we're talking about a graph, when I say the word graph, we are excluding these two types. We do not want to talk about these two types. So when I say graph, we mean simple connected graph. So again, these arise in applications, but the algorithms to deal with them are significantly more complicated. So we're just going to say, hey, we're going to sweep those under the rug and not worry about them, right? Make our life a little easier. Because we ultimately are building up to a specific type of graph that we want to talk about, and it satisfies these properties anyway. So one thing to note here about graphs is that it doesn't matter how we draw them, to a point. So I'm going to redraw this example here to demonstrate what I mean. So we had A, B, C, D, and it was connected like this. But let's add these connections too, right? They cross over top of each other. So now we've got this graph. So there are actually many ways to draw this. So we could draw it like this. So I'm going to do A, B, C, D. So then A is connected to B. A is connected to D. C is connected to B. And C is connected to D. And we're done. Right, so this looks different, but it still captures the same information, right? In the sense of, if I start at any one of these vertices and try to go to any other one, I can take the same paths, right? I will visit the same destinations. I have just drawn it differently. We could also draw this as, this is a terrible way to draw a graph, but you could do it. So A is connected to B, and C is connected to D, A is connected to D, and B is connected to C. So I guess that's not actually a terrible way to draw this one, but these are all the same, right? They all describe the same information. So graphs can be drawn many different ways. So long as we preserve or keep the edges, or let's say the vertices, and edges connecting them the same. So there is a fancy math word for this, which when you spend enough time in math, you see it literally everywhere. I say, when I was doing my undergraduate degree, we were talking about this word all the time, isomorphism. It just means same. So these two things are the same, right? These are quote unquote isomorphic. We won't use that word. That's why I have it in parentheses. It just means these graphs are the same, right? They do not look the same, but they have the same information, right? They are in some sense the same thing. So another important property of graphs is something called degree. And something funny about discrete math and graph theory especially is we borrow a lot of terminology from regular graphs. And some of the terminology is stuff that's like scary in regular graphs, but here is like kind of mundane. And degree is one of those, right? It's not like a polynomial or anything like that. So definition, the degree of a vertex, which I'm saying vertex a lot because it's a math word. Again, just remember, it's just one of these nodes, it's one of these points. It's a big fancy word for something that's relatively simple. So the degree of a vertex is the number of edges coming out of it. There's also the concept of the degree of a graph. So the degree of a graph, it's just take a look at all the vertices. What's the biggest degree amongst them? Is the biggest degree amongst vertices. So let's take a look at this one. We're going to go up to this one that I have up here. So we can label this, right? How many stick out of this? 2, right? So the degree of this is 2, 2, 2, and 2. as an example. But let's look at one that has like differing degrees. So let's look at the following graph. I want to make sure I have to look at this a lot because freshly made notes, hot off the presses. I love getting a laugh from my jokes. I'm very funny. Give me some credit. So let's say we're looking at this graph, right? So we can ask what the degrees of all of these various vertices are. So the degree, and this is the notation we would usually use, we'll say degree of vertex. So just like a function, right? Like if you had a graph data structure, degree is something you would define on it, right? And it would be a function like this. Again, 2. There's 2 vertices that stick out of that. The degree of B is also 2. There's 2 that stick out. The degree of C is 3. There are 3 edges that stick out. And the degree of D is 1. And if we want to call this whole thing graph G, then the degree of the graph is also 3, right? It's just the biggest one amongst those. So we often end up talking about degree because there are a lot of results that depend on the degree being a specific thing. So either the degree of the graph is bigger than 2 or something like that. A lot of results will say if that's the case, then the following is true because of a reason. Generally speaking, when degrees are even, things behave a little nicer, that sort of thing. So we often refer to the degree very specifically. Okay, so we've already kind of started doing it. I had those 2 graph types that I was like, hey, we don't want to talk about those, right? The idea of graphs that are not simple and graphs that are not connected, we ruled those out. But there's like so many ways to classify graphs. So there are so many classifications of graphs and types of graphs. Like I could spend a month talking about the various types, and not just me talking about them and being like, hey, here's another type of graph, and then you're like, great, Travis, I'm so bored, please stop. I could do that and then say, and here is why this type of graph is important, right? This specific subtype of graph goes to this specific application, and they use it all the time in that application, right? This is why we care about it. So I'm going to focus in on a few of them that I think are interesting. Again, this is that situation where, you know, you do some exercises and maybe think about the algorithms and you're like, that wasn't that interesting. That's good to know because then it means I will replace it with something else, because there are, again, so many different types of graphs that I could just replace one of them with another one and be like, all right, well, this has another interesting application, and we'll talk about that instead. Like an example that I was considering talking about, but didn't, simply because I was like, man, that's another one of those big math words that I would just be throwing around a lot, and I just don't want to do that. Is Hamiltonian graphs and Hamiltonian cycles. It's a specific type of graph that has a lot of applications. But then I was like, it's sort of like when I said the universe of discourse. I was like, that makes me sound like a jackass. So just saying Hamiltonian a bunch of times, I was like, I feel kind of like a jerk doing that. It just makes me sound like a hoity-toity math guy. So I excluded it. So I tried to pick ones that I think are interesting, but also still, you know, accessible. So the first example I have is a directed graph. This one sort of makes a lot of sense and has very obvious applications. So a graph is called directed if, okay, well, we still have a lot of the same ingredients. There's only like one minor change here. Oh, I already have if. If we have some vertices, we're calling them V, and some edges, which now they consist of ordered pairs. So the original definition, we said we don't care about the order. A comma B, B comma A, same thing, doesn't matter. Now we're saying we actually care. So we care about ordered pairs rather than unordered pairs. So remember, this means A comma B is not the same as B comma A. Right? These are two different things. Think like coordinates in space, right? 2 comma 3 is not the same point as 3 comma 2. So technically, in a sense, sort of like the simple and connected, this graph is called undirected, but this is the one that we talk about more often. So rather than always saying undirected versus directed, we just say graph and directed graph. We distinguish this one. So technically, the previous definition is undirected. But we don't distinguish. Or we don't say that. So if you see graph, you can assume undirected. We will distinguish directed. If you're really pretentious, you'd call it a D graph. Which I like to think I'm not pretentious. Okay, so let's just look at some examples of this, and you'll see why we call it a directed graph as soon as we write down an example. So suppose we've got the following vertices, A, B, C, and we've got edges, A comma B, B comma C, and C comma A. So now, again, they're ordered pairs. So the ordering here matters. This actually is saying from A to B, right? So what does this look like? Well, we got our vertices. They're always the same. We just draw them. A, you know what? I'm going to reverse the order. A, B, C, just to indicate it doesn't matter how you draw them. So this is saying go from A to B. But when we care about direction, we just draw an arrow saying like that's the direction it's going, right? So this is saying we go from A to B, which means we cannot go from B to A. All right, now we go from B to C. And then we go from C to A. All right, so we've got these arrows going along. So another example here. I'm just going to write down B is A, B, C, and D. And E is, this one's going to be a longer one, A comma B, A comma C, B comma C, C comma B, C comma D, and D comma B. So we just go through the motions, right? We just say, okay, well, we've got these 4 vertices, A, B, C, D. And we say, all right, A goes to B, A goes to C, B goes to C, C goes to B. So we take the same path, and point like that. And then C goes to D, and D goes to B. So we have these two graphs here. So there is actually also something that distinguishes these two. And since we're not going to focus too much on directed graphs, I'm not going to draw too much attention to it. But I kind of want to point out that directed graphs are more complicated, obviously, because we have directions now, right? So that means some of the things that we've previously mentioned don't really work quite as much. Because now if I said, well, what do we mean by connected? Well, the intuitive idea of connected, both of these are, right? There's lines connecting all of these dots, right? And that's usually what we like when we think of the first example, we have those sort of two distinct chunks, right? They were very obviously disconnected from each other. But with directed graphs, there is an extra little wrinkle here. So if we look at this graph and we start anywhere, we can actually get to anywhere, right? If I start at A, I can go to B, and if I want to go to C, I go like that, right? We've sort of got this loop here, so I can get from anywhere to anywhere. But then we take a look at this graph, and so I start at A, well, I can get to B. If I start at A, I can get to C. If I start at A, I can get to D pretty easily. But now let's say I start at D. Okay, well, from D, I can get to B, great. From D, I can get to C, but from D, no way of getting to A, right? I actually can't get there because this only goes this direction. So once you leave A, you can't get back to it. So this is what's called weakly connected. And I'm putting it in parentheses just in case you run into it. This is strongly connected. And so it's funny because for a lot of things in math, when I say this, I'm putting it in parentheses in case you run into it. You're like, yeah, Travis, though, when am I going to run into it? So with most of these topics, I can't say for certain. With graph theory, you are probably going to run into it because almost everything in computing boils down to a graph. Like just think of a program. The structure of a program and how it runs is a graph, right? You start at your main block or your initialization block, and then branch out from there in a bunch of different ways, right? And you have paths back and forth and all this other stuff, right? And along those paths, you have computational time and stuff like that. So like you can organize most things as a graph. And a lot of algorithms are abstracted as graphs. So when you think, how can I lay this out as a graph? It can actually help you tackle problems pretty often. So that's why I'm saying that, because just if you're reading, it's entirely possible you'll be reading about some way of solving a problem, and then someone will be like, yeah, well, if you just visualize it as a graph, and then they'll be like, and since it's strongly connected, blah, 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 and you'll be like, well, Travis mentioned that once. So what the distinction here is, weakly connected, if you just drop the arrows, then we have a connected graph, right? It's connected in the intuitive sense, right? There's lines connecting all of the dots. Strongly connected is the same as how we defined it before. You can get from any node to any other node. So there's that distinction, right? If you drop the arrows, you got something that looks intuitively connected. This means you can get from any node to any other node. So you can think of a lot of situations where a directed graph kind of underlies the structure. The sort of intuitive one is just think of the road network in a city, right? There are lots of one-way roads. So you can represent a two-way road and you can represent a one-way road. So in this very simple case, if I were planning my city and this were the graph of my road network, I'd be like, oh, damn, if you leave A, you can't get back to it. That's bad. We got to fix that, right? In theory, this never happens because we've all lived in cities and there's areas of the city where you're like, wow, it's a living nightmare to get around this area. But in theory, if you draw the directed graph of your road network, you can analyze, hey, are there any paths from nodes that are nightmarishly long, right? Just think of like you're driving around, like there's some roads in Edmonton downtown where you're like, okay, I just want to turn around, and you have to go down like 10 blocks of one-way street before you can turn around. And you're like, why is it like this? If they had done this, they would have spotted it very quickly. They would have been like, wow, these nodes have like 11 connections between them. We should fix that. We should add like somewhere in the middle an extra road. So like in city planning, these graphs appear a lot. In fact, if you look at some of the software, it actually just is a graph. So this is what I mean, right? These crop up everywhere. They're not just, math for math's sake. If we try to think abstractly in terms of graphs, we can actually visualize and solve a lot of problems very easily, which is pretty nice. Another example of a graph that comes up a lot, or a type, is the idea of a weighted graph. So a weighted graph is a graph that has weights. Either the vertices have them, or the edges can have them, or both, right? It doesn't matter. And so when we say weights, we mean some way of sort of prioritizing, right? So either higher or lower weights would be considered a better situation to look at. So edges, or edge weights, are typically like distance or time. So think of, you've got your program, you have a bunch of subroutines in it. You want to figure out what's bogging down my program. If you visualize it as a graph, you can find the bottlenecks, right? There'll be some edges will have like, it'll say like 40 milliseconds where everything else is like 1 or less. And you're like, oh, wow, that's really taking a lot of time. Why? And then you examine it. But there are lots of other situations where you would do this. When would vertices have weights? Vertex are typically like rankings or priorities. So think like, I'm building a graph of, I'm going on a trip to, Europe. I have an order, a priority system of like, I want to visit these countries in this priority. So how do I plan my trip to hit all of those? Like maybe they're all over the place, right? So you plan your route like that. And then eventually you're like, I don't want to visit these lower priority cities because I'm running out of time, right? So that would be a situation where you would weight the vertices, right? The cities themselves have weight and you want to organize them like that. When they both have weight, that's when things start to get really nightmarish. Okay. So the way we would generally indicate this on a graph is the sort of obvious way, right? Like, you know what? I was going to say, I'm just going to recycle this graph, but I have a philosophy. If I'm going to make you write it, then I'll write it too. So consider the following graph. We've got A here, B here, and C here. And so the way we would indicate weights on an edge is just by drawing them on the edge, right? The way you would indicate weights on a vertex is probably, rather than, writing A, you would write the weight itself, or you could say like A5, right? You would just put the weight in it. But we're just talking about edges here. So like I said, edge weights are typically distance or time. So if we think about that, in this case, well, if we wanted to go from A to C, the quote-unquote fastest or most efficient time is actually to hit up B and then go to C, right? Because that would have a weight of 2 plus 3, which is 5, right? So paths from A to C, we can go A to B to C, or we can go A to C. So again, this weight is 5. This weight is 10. So this is, half as fast. Or sorry, half. So that's another. So either this is half as fast or half as long, right? It depends on what your weight represents. So you can this is kind of an important note about graphs here, right? They're abstract, right? They're not to scale or anything like that. Especially if you actually start talking about representing them as data structures in programming, there's no visual component anymore when you're programming it, right? It's just code. But they still have these corresponding components. So this is not a true triangle, right? This doesn't even make sense in terms of a triangle, like thinking Pythagorean theorem and stuff like that. So we can think of this in terms of this is a road network connecting these 3 things. There's construction along here, right? So think in terms of your GPS, right? You have this exact route. You're here and you want to go here, and your GPS is like, actually, you should detour. And you're like, why? And you look, there's like a horrible accident here. So going this way would be way slower, right? So even though this is a longer looking distance, it's shorter, right? So that's where weight comes in when you really think about it. Is sort of planning transit routes using like your GPS essentially does a much more sophisticated version of something like this to plan routes and correct routes when things happen. So that's where weighted graphs would come in. This next section, I did this in my other class too, but I realized I should probably make this the first thing I talk about. For one main reason, it's that I'm about to talk about a little bit of history. Not in the sense of like a history class, but just like this is a historical thing. It's where graph theory came from. And it's sort of an interesting problem. It's called the Bridges of, I have to remember the name, Königsberg, 7 Bridges of Königsberg. So Leonhard Euler was a mathematician in the 1700s, late 1700s. And someone proposed a problem to him. He said that they were like, okay, we have this city, and I have to, please excuse my drawing. I'm not an artist. So it looks like this. There's an island there. So we've got a city that's sort of subdivided into chunks like this, right? We've got a landmass here, a little island here. It turns out this is also an island. And then we've got the landmass here. This city still exists. It's no longer matching this exactly, apparently. They've torn down some of the stuff, but the landmass still exists. And so in this city, there were 7 bridges. And they connected to the landmasses like this. There's 2 here. There's 1 here. 1 here, and there's 1 here. So we have these bridges in this city with these landmasses. And someone went up to Euler and was like, hey, I want to take a tour of the city, sort of hit up all of these areas. But just as an interesting, twist on the problem, I want to visit every single bridge once and only once, right? I don't want to go across the same bridge again because I've already seen it, but I do want to see every bridge, right? Because they're all constructed differently and he wants to see every bridge. So we take a look at this and we start, he sits there and he's like, all right, let's try and solve this. Let's say I start here and we go across this like this. Oh, we're stuck. Right? Okay. Well, let's start here maybe, because this is the bridge we missed, and we go across. We're stuck, right? So he went on and on with this, and he realized I'm getting stuck a lot, right? And if you try to solve this problem, same problem, right? You'll be like, I keep getting stuck. So because he was a mathematician, he started thinking, well, what's going on here, right? There must be some underlying reason why I seem to be unable to solve this problem. Either there's only one solution and it's super not obvious, or there is no solution and there's a reason why there's no solution, right? That's generally what we do in math. We try to abstract a problem and then say, why is there no solution? Is there some kind of pattern going on here? So what he actually did was he said, the shape of these islands and cities, they don't matter, right? All that matters is I can start here, 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 or here, right? And then we have these sort of connections. I can go like this or like this. I can go like this or like this. Like this or like this or like this. Well, that's starting to look an awful lot like this thing that we were just talking about, right? A graph. So he said, all right, we've got these nodes like this, and we have these connections. Like this. So, all right, this is sort of step one in mathematics, and honestly, this helps in programming too, is abstracting your problem, right? Really taking a look at the concrete example that you're dealing with and thinking, what's sort of lying on top of my problem? Like, what's really going on here? And so he boiled it down to this very simple structure, right? And then he thought about this even further now that he's looking at this, and he's like, okay, but like, if I started anywhere, then let's say I left this node, right, to go here. Well, once I go here, in order to leave this one, that takes an even number of bridges, right, connecting here, right? So I like, if I come in here, in order to leave it, that's 2, right? And now I came into here, that took 1, and now I've used 2 that connect to this, right? So that's kind of how he thought. He was like, hey, it seems to be that there needs to be an even number of bridges, at least in most of these, right? So it turns out, if you start somewhere and want to end somewhere else, it's okay if these are odd numbered, right? Because I leave here once, I don't go back there, right? So I only used 1 bridge. And then if I enter here, and that's where I end, I only use the bridge getting in there. I don't leave, right? So, okay, 2 of them can have an odd number, but everything else has to have an even number of these edges, right? In modern parlance, we would say the degree of these have to be even, right? But what is the degree of this? 1, 2, 3. 1, 2, 3, 4, 5. 1, 2, 3. 1, 2, 3. So by that exact reasoning, this is impossible, right? Because by his reasoning, it's okay if 2 of them are odd, right? Because I can start in one of them and end in the other one, right? And then only use 1 bridge to get out. But then, even under that, there's 4 of them and all 4 of them are odd. So it's not possible. There's always going to be some bridge left untraveled, right? Or I'm going to get stuck because I always need an even number to get to a node and then leave it. So as soon as I basically exhaust my bridges, I'm stuck, right? And so this actually led to a definition, or so I, in his original memoirs, I think he actually phrased it as like a result specifically related to these bridges. It turns out it's a much more abstract concept, the idea of something called an Eulerian trail. We named it after him because he came up with it. And it was sort of published posthumously because I think it was published in like 1820 or something like that after he'd passed away. But this type of idea actually ends up being pretty useful. So we do have a name for it. And this is what I mean. This probably should be like the thing I start with in this topic, because this is literally how graph theory started. It started from here. Someone had this problem and sort of abstracted it, and then developed theory about it. So anyway, that's a future me problem. So an Eulerian trail which some of these big math words are like that because they're named after someone who had that as their name, is a path through a graph that visits every edge once and only once and we don't care where we start or end. So this is called an Eulerian trail, which means it does not matter where we start and end, technically. there is something called an Eulerian cycle, which is starting and ending in the same place. But it's a slight modification of this. It would just say where you start and end in the same place. That's all. So what he spent all this time doing is when does a graph have these, right? Because when we know it has one, it solves this exact problem that he was dealing with, plus a bunch of others. So a graph has such a trail if and only if the degrees, is that how I want to say it? No. If exactly 1 or 0 or 2 vertices have odd degree. So in solving this problem, so if and only if means both directions, right? If this is true, then this is true. And if this is true, then this is true. He only proved one direction, which is the one that we were sort of just discussing, where if it satisfies these properties, then one exists. But if one exists, doesn't satisfy those properties, was a much harder problem to solve that took until after he was dead before we found it. But you can think of lots of situations where these come up. Maybe not where you personally would devise or solve for one of these, but you kind of naturally do it. So like imagine you are taking a road trip and you're hitting a bunch of cities. And I don't know about you, but if I'm on a road trip, I would prefer to avoid driving down the same road more than once because I've already seen it, right? Same idea here. He doesn't want to cross the same bridges because he's already seen it, right? Don't want to see the same scenery more than once. So when you're planning a road trip, you are essentially finding one of these, right? You are hitting all the cities that you want to see while not driving along the same road more than once. Although with a road trip, like let's say you're doing a cross-Canada trip and you've got all these cities, usually you would plan it like this. So it's pretty easy because it's sort of a circle like this, but we see naturally everything has degree 2. But you could change it so that like if you came to the same city again because it was just more convenient, then you have to worry about that. So anyway, these just crop up naturally a lot, just in problem solving. So that's why I thought to talk about it, and for the historical context, which I think is kind of interesting. Okay, so how about another quick application of algorithms? So ultimately, the reason why I'm talking about all this graph theory stuff is because there's a lot of interesting algorithms that come out of them. Because looking at what these are, both even in the math sense, they're pretty simple, right? It's some dots with some lines around them, right? Like they're relatively simple to grasp. So it's kind of interesting that we get some really, really useful and powerful algorithms out of them, even though they're that simple. And that the very core definition that I gave in terms of sets is actually how you tend to build these as data structures in programming. So for once, the technical math definition actually is useful. You would actually use it that way, although you would probably use a dictionary as a shortcut for, like, you would connect vertices as the key in the dictionary, and the values would be the edges connected to that vertex. So it just makes your life a little easier. But you can only get to that from understanding the set theoretic definition of it. So another algorithm that we can get out of this, which ends up having a pretty natural application, is graph coloring. So it is actually as mundane as it sounds. We're just going to color the vertices of a graph. So we want to color the vertices of a graph. But we have a condition. No two connected vertices can share a color. So like if two vertices are connected, they are definitely different colors. Where no adjacent vertices I'm going to say connected. Connected is better. Vertices share a color. So, okay, there is actually a way to do this. It's pretty straightforward. So step one is, well, pick a color and pick a vertex. Pick a vertex first. Doesn't matter which one. Now pick a color. Index it as 1. So we're gonna order the colors. We're gonna give them indices, right? We're gonna call this color number 1. Color this vertex as that color. All right. Hey, that first step's pretty easy. I can color things in pretty straightforwardly, I think. So, okay, what are we going to do next? So, choose the next vertex to color. Now, in terms of an algorithm that we would implement, we're probably going to choose one that's connected to what we just did, right? So you just colored a vertex. There's an edge connecting this one. You're going to color that one. Technically, you could just pick another random one if you wanted. But generally speaking, when we're doing this, we want to find minimal colorings, right? What's the smallest number of colorings that we can use for any number of reasons? Because using different colored paint, like using 5 paints versus 3, getting 3 paints is cheaper than getting 5, right? So lots of reasons like that. So ideally connected to the last one. Okay, so what do? We color this vertex with the color that has the lowest index. Index color. And if one doesn't exist, create it. If there isn't one, that's it. So this algorithm actually produces a minimal color set with a potential asterisk. I would need to double check this. It might depend on your starting vertex. Like if you choose an incorrect, like a bad starting vertex, you might get more colors than you might need. And there are a lot of problems that come out of this that are computationally very intensive. So a question you could ask is, you have a specific graph, and usually it's going to be a pretty complicated looking graph. And you ask, how many ways are there to color that graph? That is not trivial. That is a hard problem to solve. In fact, I think it's NP hard, if you know what that means. I think it's like an exceptionally difficult problem to solve. To the point where if you have a graph with like 30 vertices and you say, what's the minimal one? You're going to be waiting hours to get that solution. If you follow like just a naive algorithm to do it. But let's just run through this in a simple case. So we have the following graph. I gotta make sure I match these. This is our graph. So what does this algorithm say to do? It says pick a color. Wake up call. Pick a color. What should I use? Green. Everyone said a different color, so I'll pick my favorite color, which is red. This plan didn't work very well. So I'm going to pick a color, red. We're calling it number 1. And then I just pick a vertex. Pick one. Once again, disagreement. I'm going to go against the grain, and I'm going to pick one that was not said. I'm going to pick D. Being a real contrarian today. So then what this algorithm says is choose another one, right? Ideally, again, so if we were to implement this algorithm, we would choose a connected one because that's just the easiest, right? Picking a random one is a bad idea, especially if we're dealing with a connected graph. Anyway, you might as well just pick one that's adjacent. And then another color. So we'll pick blue. I'm going to number blue as 2 and pick another one. C. So we colored it blue. And now I pick another one. Well, there's only one vertex adjacent to C. It's B. I look at it and I say, okay, well, I can't color it red. I can't color it blue. So I have to pick a new color, green. Color that in. And now I go to this one and I say, all right, we're going to color this vertex in. I can't color it red because one of my neighbors is red, but I can color it blue. So I color it blue. And you can kind of see how this probably produces like a minimal set, right? Because you're only ever using the easiest accessible color. Like the one that you were using the most is the one that you're grabbing the most. So why would we care about something like this? You've seen it like a lot. Think of a map of the world or a map of the United States. Please, I don't know what the United States looks like. Close enough, right? There's Florida and other stuff. But anyway, you've got these sort of states, right? They're stuck together like this. But we can actually capture this as a graph. And we can find all the connections. And then we can start coloring this graph in using this exact method, right? So we would say, all right, pick one. Here, color it red. Pick another one, color it blue. And then pick another one. This one has to be green. This one can be red. And then this one is blue, and so on and so forth, right? And so this color is a map of the world or the United States or whatever using a minimal set of colors. And if you just look at most maps, they're colored like this, right? So this is an algorithm that is regularly used for this specific application. And I mean, there's lots of other situations where we use it. So instead of coloring, as an example, you could think of like groups of people, right? You've got like, 50 students and you want to distribute them in a certain way. So you just, you create a group and then now you go here and you have to create another group. And then you go here and you have to create another group. And then you go here and, I can put the first group there and so on and so forth, right? So the way of like colors are just groupings, right? They're a way of grouping things and assigning them to a specific node or stop or vertex and just doing it in a systematic way. So this is just an example of like an algorithm that I saw that I was like, hey, graph coloring is kind of neat. And there's an obvious application of it where you can imagine an algorithm that would do that on a computer. And there are other applications of it too that are much more involved. But these were all just like fun little things that I saw to just sort of motivate other like more accessible ways for why we would care about graphs. The main meat of what I want to talk about is what I would call the main graph that we care about in computing, and that's trees. So trees in computing are a very important data structure for solving very specific problems. An example of which would be binary search trees are useful for binary sorting, and binary searching is very, very quick. It's O of log n if you want to find numbers in a binary search tree. So it's a very, very efficient way of organizing your numerical data. But what is a tree? And I'm going to put this in parentheses because technically in graph theory, what we're talking about is a rooted tree. There is something called a tree that does not actually have a root, but we're talking about this. It's a graph with two properties. The first one, well, I called it a rooted in parentheses. So we have something called a root. There is a vertex called the root, from which all edges and vertices originate. All edges and vertices originate. And that may not be directly, right? It might just be a path, right? There's a path from the root to everything, like in sort of a branching way. The other one, if there are n vertices, there are n minus 1 edges. And this last condition, technically, there are like a lot of different ways to describe it. I think one of them is if the graph is connected and there are no cycles, then it's also a tree. But anyway, there are like 5 or 6 different conditions here that you could use instead. I think this is the most accessible one, though, because you literally just count to make sure that you're in that situation. So let me just give you an example of a tree. And you'll see why we call it a tree. So something like this. Got 2 there, there. So it doesn't matter what I call these: A, B, C, D, E, F, G, H. So it looks like this. And you're kind of seeing a tree-like structure here, right? So this up here, we're calling it our root. And we see that everything sort of, in a sense, originates from here, right? It's all kind of branching out from that top node. There, see, I'm doing it. I'm talking about trees. I'm calling it nodes. And let's see if we satisfy this property. 1, 2, 3, 4, 5, 6, 7, 8 vertices. 1, 2, 3, 4, 5, 6, 7 edges. So we satisfy this property. So this, by our definition, is a tree. And there are a couple other pieces of terminology here related to trees that I want to talk about. If a vertex has degree 1, we call it a leaf. So going into that tree aesthetic here, this is a leaf, because there's only one vertex from it. This is a leaf, and that's a leaf. Now, something I want to point out about this. This makes sense. We called it a leaf, right? It's at the edge of a tree. Yeah. Why'd we call a root the top of a tree? You look at a tree, the roots are not at the top of it. They're at the bottom of it. I don't know. Ask computing scientists why they did that. Who knows? So the root is the only weird word here. Everything else kind of makes sense. I think I don't want to go too much more into it. There's some other definitions I want to talk about. I'll worry about them on Wednesday. But we have the idea of parent and children, and they are what you think they are. So let's take a look. I'll just ask people, like, without even defining what it is. This node B right here, this vertex. What's its parent? What are its children? Yeah, right. It is what you expect it to be. The definition is a little bit wordy, but parent and children, they make sense. So B, A is parent, and D, E, children. These end up being kind of important because, so when we think about this structure, if we were to do things with this, we got this top one here, right? Cover it up. What do we have now? Like, we'll cover up this edge and these vertices. We have 2 trees, right? So it lends itself really naturally to recursion, right? You do something to A, cover it up, you got a left branch and you got a right branch. Do the same thing to the left, do the same thing to the right, right? It naturally lends itself to recursion, which is why this fits in naturally after talking about recursion, because there's a couple of algorithms we were going to talk about that recursively deal with trees. So my goal again, weird because you guys have already finished your Python. So in some sense, that makes it easy. In some sense, that makes it worse because at the end of the term, I'm going to ask you to do some programming. My hope is to get you to mess around with some trees. I will not ask you to build a tree-like structure because I'm not going to assume that you have deep knowledge of how object-oriented programming works yet, because you would have to build an object that is a tree. I will provide that to you and then just say, all right, implement some of the algorithms we talked about. Like, we're going to talk about breadth first search. We're going to talk about depth first search. We're going to talk about if you have a binary search tree, how do you search through it to find specific numbers. A couple of really fun, simple, recursive algorithms. Most of the work is in building the data structure, the tree itself. So when I assign those exercises on the group projects, I will give you the underlying data structure. If you want, I encourage you to poke around and see if you can see how it works and why it works. It won't be super complicated in terms of programming, but I will not expect anyone to understand it. It will not be fundamental because, again, it needs object-oriented concepts. And I don't know, in Python, did you spend much time on object-oriented programming? No. A little bit? Okay. So, yeah, basically what I'm going to do is I'm going to say, hey, I have created an abstract data structure. It's called a tree. Here's how you create a tree in the language or in the stuff I give you. Now just run this algorithm on the tree, right? So I won't ask you to deeply understand it, but we'll see how that goes because I just want to show you that this stuff has like a lot of applications in programming, and it's actually you may or may not have the requisite knowledge to really deeply understand the implementation, but you'll look at the code and you'll be like, there's not a whole lot here, right? Like it sort of lends itself naturally to being implemented in programming languages. So I just think it's interesting because everything in programming can kind of be boiled down to a tree. There's trees underlying everything. There's graphs underlying everything. So it's just one of those topics that I feel like I want to delve more into than a week, but we only have a week right now. So that's where we're going to leave it. But next Wednesday, we're going to talk about a bunch of algorithms, and then I'll give you assignments on just basically doing them by hand just to understand them, so that when it comes to the programming assignment, you can actually implement them not by hand and more efficiently. Anyway, that's all I have for now. And I'm pretty happy that I basically, in a weekend, produced an amount of notes that fits the exact amount of time I want. So I'm pretty happy with myself. I did some, by some metric, I did good.